let's talk about calibration curves. We'll start by defining what is a calibration curve. Now, calibration curves are usually applied in the topic UV-Vis spectroscopy, where it is a plot of absorbance on the y-axis versus concentration on the x-axis. And this plot of absorbance versus concentration is usually used to determine the concentration of an unknown analyte. And I'll talk about that as we look at our graph. So this is an example of a calibration curve where we see a linear relationship between concentration and absorbance. That is, as the concentration of the solution increases, its absorbance increases. If we have an unknown substance whose absorbance we can determine, we can use the calibration curve to work backwards and work out its concentration. Now, how is a calibration curve plotted? Where were the plot points obtained to draw this linear relationship between absorbance and concentration? This plot here is obtained from using something called a standard, where standard solutions are prepared beforehand, which are solutions of known concentrations, and the standard solutions contain the analyte which is found in the unknown. So these solutions whose concentrations are known and the absorbance can be determined can be used to create this calibration curve. We're going to pause to look at how do you prepare a standard solution which is needed for plotting a calibration curve. So you are given your analyte. You're going to weigh X grams of your analyte. It can be 1 gram, 2 grams. You're going to go with X grams here. Your X grams of your analyte you have to dissolve. You can use a quantity of distilled water. So you're going to add 50 cm cube or 100 to a beaker. You have to stir to dissolve or completely dissolve your analyte. You are to then pour your solution into a 1000 ml volumetric flask, and then you're going to add distilled water into that beaker and transfer its washings into the same volumetric flask using a filter funnel. Next up, you're going to fill that volumetric flask up until the graduated mark with distilled water. Last but not least, after you have made up your standard solution, you still have to stopper and mix to ensure that, to ensure that there is complete mixing or dissolving of the analyte into the solvent, which in this case may be water. And that is how we prepare our standard solutions. We can change the quantity, which is the mass of our solid, which is dissolved into a fixed volume of water to create standard solutions of different concentrations. Now, what we want to do now is discuss aspects of the experiment, that is, preparing of the standard solutions, use of instruments, all of which is involved in the preparation of this calibration curve. So we want to talk about our graph before we move into those aspects, where in the analysis of a graph, we can look at the gradient of the graph, and the gradient of the graph will be a measure of the sensitivity of the experiment. So here, where we have our calibration curve, if another person did the exact same experiment and they got different values, and the different values can be expressed in a different linear relationship, and we were to compare one curve to the second curve, the curve that has the higher gradient would be the more sensitive calibration curve, where this higher sensitivity of that calibration curve will indicate that this method has a lower detection limit and a lower interference. What is the detection limit and interference, you might ask? Let's go on to talk about that. The detection limit of an experiment represents the lowest concentration of our analyte which can be detected. Let's say, for example, we have our UV-vis spectrophotometer and we need to detect iron concentrations in ppm, which is parts per million. Our detection limit will be the lowest concentration of iron that our spectrophotometer can detect. Now, how is the detection limit determined? It is done so using a blank solution. What is a blank solution? A blank solution represents a sample that does not contain any analyte. Now, when a blank solution is run, let's say in the electronic device, or in our case, our UV-vis spectrophotometer, if the blank solution gives a reading, that means when we perform our experiment, we would deduct the signal created by the blank solution from our experimental values. So, for example, if you determine absorbance for your different standard solutions, you would deduct the absorbance of the blank solution, and these values we would refer to as corrected absorbance. Now, the blank solution is very important, and I'm just going to highlight what is the significance of the blank solution. So we just talked about one, which is that it is used to zero the instrument, that is, give us corrected absorbance values, and it is used as a means of quality control, meaning that you can use it to check for contaminants. So if there is a signal from our blank solution, that means what we contain in our sample to be mixed with the analyte contains contaminants and might need to be changed, and our blank solution hence establishes a detection limit for our experiment. So, given that the detection limit is the lowest concentration of the analyte that can be detected, we can now reflect on what sensitivity, detection limit, and interference mean. That is how are they related. And we're going to do so by just looking at what is considered to be interference in an experiment. So interference, as you would know, in most of your experiments you have done, it's usually the presence of some sort of contaminants, whether it's in the solvent, the reagent, the glassware being used. Where it refers to spectroscopy, it can be some sort of spectral interference or maybe a background noise or signal, and it is the presence of interference which will change our detection limit and hence the sensitivity of our experiment, meaning that our experiment will have a lower sensitivity where the detection limit is not very low, and as a result of that we have a high amount of interference. So to clarify once more, if in our experiment there's a low degree of sensitivity in our calibration curve, It indicates that the detection limit is not as low as a concentration which would give a great amount of sensitivity to our experiment, and a poor detection limit would be as a result of a high amount of interference in an experiment.